Hi and welcome to Ease Genetics. Today's video topic is pedigree, genotypes, determination. In this video, we will see how to determine individual genotypes of a certain trait in a pedigree. Before we start determining the genotypes, there is one important thing that you have to keep in mind. To determine the genotype or any analysis, remember sometimes you have to go back and forth between the parents and the offspring to determine an individual genotype when a complete dominant interaction between the alleles for a gene exists. As usual, we start with an easy one, the guinea pig coat color pedigree. Let's use big B for the dominant black allele and small b for the recessive white allele. Starting with the first individual in the first generation, I1, it's black, so we know it has at least one big B allele to become black. But what about the other allele? We don't know whether it's a big B or a small b. So at this stage, for the second allele, we mention a dash. The dash means it could either be big B or small b. One important thing that I want to tell you here about complete dominance is that besides all types of interactions between the alleles, only with complete dominance we have a little problem with the dominant phenotype, which is we can't determine whether the dominant phenotype is homozygous or heterozygous. While in other types of dominance interactions, each phenotype has its own genotype. So by seeing the phenotype, we can reach to its genotype except complete dominance. Back to the pedigree, I2 is a white female guinea pig, so we know its phenotype. It's small b, small b. Let's move to the second generation, starting with II1. It's a black male offspring, so it has a big B. As I said earlier about back and forth, let's get back to its parents. I mentioned the path to its parents in red. We know its father, I1, has at least one big B, but its mother only has small b alleles. As offspring receives one allele from its father and one from its mother, the only chance for II1 to become black is to obtain a big B allele from its father. So what it receives from the mother will be small b. So we know II1 is heterozygous, big B, small b. II2 is a stranger in this pedigree, as it is not connected to any pig above it. It's black, so we know it has a big B allele, but we don't know if it's homozygous or heterozygous. Like I1, we give a dash for the second allele as unknown. II3's condition is the same as II2's. It is a black stranger pig, so we also mention it as a B dash. And II4, which is a female offspring pig, is the same as II1. It received a big B from its father and a small b from its mother. So it's a black heterozygote. Now let's go to the third generation, starting with III1. It's black, so it has a big B allele. Now let's go back and take a look at its parents, II1, the father, and II2, the mother. I show the path in red. Both are black and have the big B allele. Whom did II1 receive its big B allele? We don't know. Maybe it got the big B from its mother. So what did it get from the father? Big B or small b? We don't know. If it got the big B from its father, II1, what did it get from its mother? Big B or the dash that we even don't know if it's big B or small b. So II1 will remain B dash until we get more information that leads us to its genotype. II2 also has the same situation as they are siblings, so this is also B dash. Moving to III3 is getting to another family whose path to its parents is in red. III3 is the offspring of different parents. II3, a B dash, and II4, a black heterozygote pig, just like the two previous pigs, II1 and II2. III3 is also B dash, as we only know it's black and can't determine what the second allele can be. Now, III4 is a white pig, so its genotype is small b small b. To receive these two recessive alleles, it must get one small b from each parent. By looking at its parents, the father II3 is B- and the mother is heterozygote, so we know it received one small b from the mother. So the second small b must have been received by the father. With this information, we now know exactly what the father's dash is. It is a small b and can't be a big B, and for that, the parents were able to produce a white pig. The father, who is a stranger in this pedigree, is a heterozygote black guinea pig, so I replaced the dash with a small b. I mentioned it in red just so you can better focus on it and also emphasize that it was determined by its offspring. Finally, III5 is the same as III3, and although we determine its father's genotype, we can't determine the II5 and also II3 genotypes because of its parents' genotypes. It can be either homozygote or heterozygote, as we don't know from which parent it received the big B allele and what allele it received from the other, which could be either big B or small b. Complete dominance is a tricky type of dominance, as for two alleles we always have three phenotypes. In other types of dominance, one for each genotype, but in complete dominance there are only two phenotypes and two of the genotypes share the same phenotype. As you see in this pedigree, due to the information regarding the relationships, we only determine 5 out of 11 individual genotypes. The most important issue in pedigree and genetics in general is the number of offspring. The more offspring we have, the more information we will have to analyze the data and reach a better result and understanding. For example, if in the part of the pedigree that I have highlighted in yellow, the parents II2 and II3 had produced more offspring, let's say 10 or more, and they were all black, we could have concluded that regardless of what allele the offspring received from its father, the mother had no allele except big B, and that was why all the offspring became black. Now, in this slide, I focused on this part of the pedigree and assumed 10 black offspring for parents II1 and II2. We can use the basic monohybrid crosses to see how the pedigree fits them. By considering the second and third generations, it matches only with the second cross, big B with big B small b, and all the offspring will be black. But remember, in the original pedigree there were only two offspring, and as the number of offspring is low, we kept them as B-. Who knows, maybe if the female gives birth to the third or fourth piglet, it might even become white. As I said earlier, traits with complete dominance might get tricky, as the dominant phenotype can either be homozygous or heterozygous. But for all other types of dominance interactions, each phenotype has its specific genotype. So the phenotype of each leads us immediately to its genotype. Here we have a pedigree for flower color with an incomplete dominance interaction. As mentioned in the instruction of the pedigree, you see the red flower genotype is big R, pink flower is big R, and the white flower genotype is small r. Under each individual, I mentioned its genotype, and as you see, no unknown genotype exists. They are all determined. In my video, Pedigrees, Introduction and Basics, which you can find its link in the description, I introduce you to my imaginary family, the Smiths. There I also showed how to insert their blood types in the pedigree. And this is how it looks. I chose a pattern for each blood type shown on the top right, and I applied each individual the pattern that matches their blood type. Now let's start determining their genotypes. Before we start, let me remind you that the ABO blood type in humans is a multi-allelic trait with 3 alleles. A, B, and O. The interaction between these alleles is also interesting. Alleles A and B are dominant over allele O, while the interaction between alleles A and B is codominance. As you see, for 3 alleles, we have 6 genotypes, but due to the alleles interaction, there are only 4 phenotypes. We have no problem with individuals with blood types AB and O, as their phenotypes represent their genotypes. But for individuals with blood types A and B, just by their phenotype, we can't assign their genotype because they can either be homozygous or heterozygous. So their family relationship and information might help us determine their genotype. Starting with I1, he has an AB blood type, so we know his genotype is AB. Also, I2 has an O-type blood, so her genotype is OO. Heading to the second generation, II, the first individual, II1, has an A-type blood group. By following the path to his parents, shown in red, we see that he must have received his A allele from his father, as his mother carries only O alleles. So what he received from his mother could be nothing but an O allele. So II2 is a heterozygous A-type blood group. Individual II2 has an O-type blood group, so her genotype is OO. She is also a stranger in this pedigree, and you see no line coming down to her. Individual II3 has a B-type blood group, and we have to find out if he is homozygous or heterozygous. Following the red path to his parents, he received his B allele from his father, and as his mother is an O-type, he received an O allele from his mother, so his genotype is BO. Individual II4 has an A-type blood group, so she has an A allele. But as she is also a stranger in this pedigree and there is no information about her parents, we have to leave her as A-. Now to the third generation, III, individual number 1 has an O-type blood group, so her genotype is OO. Now just for a moment, let's check her parents. I turned the path to her parents in red. As you see, her father's genotype is AO and her mother's is OO. As you see, it is possible. She received one O allele from each of her parents. Individual III2 has an A-type blood group. Following the red path to her parents, she should have received her A allele from her father. Therefore, she received an O allele from her mother. She is a heterozygous A-type blood group. Individual III3 has a B-type blood group. This is interesting. Following the path to her parents, her father's genotype is BO and her mother's is A-. As she is a B-type, she received her B allele from her father. Now, what she got from her mother? Obviously not the A allele, because in that case, her blood type would have become AB. So the only possibility that she becomes a B-type blood group is that she receives an O allele from her mother and her mother remains as an A-type blood group. So now we not only determined her genotype as BO, but we also determined her mother's genotype as AO. As you see, individual III4 has an AB-type blood group. Also, by following the red path to his parents, you see that he received his A allele from his mother and his B allele from his father. Finally, III5. She is just like her sister III3. Her blood type is A, so she received her A allele from her mother, and to become an A-type, she must have received her father's O allele. And here we are. The genotypes of the Smiths family are determined. In some pedigrees, you might see that some A and B types genotypes might remain as A- and B-. We were lucky with this family to determine all their genotypes because the pedigree information was enough. If you found this video helpful, give it a like, share it with your friends, and subscribe to Ease Genetics for more engaging content. Have questions or topics you'd like me to cover? Drop them in the comments below.